Hi, my name is Joseph Moon and this is Lab 4 Oscillations. So the sections I will cover are Introduction, Models, Experiment, Code, Discussion, and Conclusions. The purpose of this lab is to study the motion of a mass spring system with the mass oscillating in an arc. The system in question is the spring mass Earth system, and this means that the surroundings is none or nothing because it is an isolated system. The goal is to determine whether the model follows the energy principle, and then a preview of the results is the model follows the principle because the system's total energy remains constant at 0 joules. Some models we will need to know are Newton's second law and energy principle. Newton's second law, as stated before, is the net force is equal to the change in momentum divided by the change in time. And then we can derive the velocity and position update formulas from this second law to find the initial velocity and position. The energy principle states that systems' change in energy is equal to the sum of the work done by the surroundings and other energy transfers done with the surroundings. And some examples would be thermal energy. So, experiment, we have the video and the mass is on a spring oscillating in position. And we have the object's mass of 0.402 kilograms, the stretched length of 0.7 meters in initial position at this position marked here, and then in initial velocity here. So for our experiment calculations, before using the computational model, I calculated the period by taking the average of 5 periods in the y direction and then found the period to be 1.5196 seconds. For the spring stiffness K, I said that T is equal to 2 pi times square root of m divided by K and solved for K and then plugged in the values for mass and period and found that the spring constant is 6.866 newtons per meter. For the relaxed length, I used the net force formula in this case, and I plugged in all my known values, rearranged to solve for L naught, and I got that L naught is equal to 0.126 meters. Here's my code, and the top is the ball's mass. I have the initial position and velocity of the ball, the constants below, and then the energy equations for kinetic energy, gravitational potential energy, spring potential energy, and the total energy. So here are some more lines of code. This is a while loop so that the code can iterate the mass spring system. The top is the initial energies. Then we have the gravitational force, the spring force, the net force, the position and velocity update formulas, and then the new energy and the change in energies. So here is the video of the results when the data is put into GlowScript. And as you can see, the model and the experiments positioned in the x and y direction are different because they are not completely in line due to the system not being completely isolated in real life. And then some sources of error include significant figures or rounding, because rounding the values during calculation and rounding to position data may have caused the accuracy to deviate. Another source of error is inaccurate position tracking when using tracker. There are many time frames to track the position of the mass, and each point placed may not be exactly on the center of mass or the same point at each time frame. And then the unrealistic isolated system assumption, this is that in reality there will be work done by the surroundings because the system is not actually isolated. Is the energy principle satisfied? It is satisfied because no external forces affect the isolated system, and as you can see in this graph, although there are different kinds of energy acting on the system, there is a zero change in energy because delta E here is a straight line at 0. And then for period estimations, if you calculate the period in the x direction and the y direction, you get different period values, and this would in turn cause different spring constant values, which would mean that doing the period calculations in different directions would lead to different values.